Okay, today we're going to look at section 4.4, the mean value theorem. So what we're going to do is go through a few theorems, Rolle's theorem and the mean value theorem, and discuss how important they are. The main thing to keep in mind with this is that the mean value theorem is not a theorem that we use for solving problems immediately. It's something that we're going to use to build up to later. So we really want to understand the idea. We're not going to focus on a huge amount of solving problems, just a few to understand what's going on. So let's go ahead and get started with Rolle's theorem. Now, Rolle's theorem and the mean value theorem are kind of the same. So we're going to think of this as like a way to lead up to the mean value theorem. So let's first look at what it is. Here's the statement of the theorem. We have a function f. We have three conditions on f. First, f is a continuous function on the closed interval ab. Second, f is differentiable on the open interval ab. The reason that this theorem is stated this way is because if a function is only defined on a closed interval, it can be continuous at the endpoints, but it's not possible to be differentiable at the endpoints. And then the final condition is that f of a equals f of b. Then what the theorem tells us is that there's at least one number c in between a and b where the derivative is 0. So let's go ahead and take a look at this in a little more detail with some graphs. So here's an example of a function. Here's f of a, here's f of b. You can see they're equal. The function is continuous and differentiable. In order to start and end at the same height, we have to turn around somewhere. So we need to have the derivative be 0. Maybe the function goes up, maybe the function goes down, okay? Maybe it does both. Maybe it goes up and then comes down, and then there's more than one point in between where the derivative is 0. This theorem just says that the function has at least one value where the derivative is 0. Okay, so let's take a look at an example illustrating the mean value theorem, Rolle's theorem. First, let's verify the hypotheses of Rolle's theorem. Now remember, there were these three hypotheses. We need these three things in order to apply the theorem. Okay, so first we need that f is continuous on our interval, in this case 0 to 3. Okay, and it's a polynomial, so it just is, right? We know that polynomials are continuous everywhere. Next, we want to show that f is differentiable on this interval. And the easiest way to show that something is differentiable is to show that its derivative exists. So what we're going to do is say, well, I know that the derivative, f prime of x, is 2x minus 3, and this is clearly defined on the interval 0 to 3. Okay, and then finally we need f of a, which is 0, to equal f of b. Well, f of 0 is 0. F of 3 is 3 squared minus 3 times 3, which is 9 minus 9, or 0. So f of 0 equals f of 3, and now we have all three conditions. Okay, so then the conclusion is that there is a number in the interval 0 to 3 with f prime of c equals 0. Okay, now let's look at part 2. Find that value. Okay, well, we know that f prime of x is 2x minus 3. We just need to find the values of this derivative that are equal to 0. So we solve f prime of x equals 0. So we get 2x minus 3 equals 0. So x is 3/2. So c equal to 3/2 is the value we are looking for. And that's it. So that's Rolle's theorem. And again, the idea is just if a function has the same height at 2 points, that means it has to turn around. And as we talked about in section 4.3, critical points are the places where a function can turn around. They're going to be where the derivative is either 0 or undefined. But since this function is differentiable, it can't be undefined. So if the function turns around, it's got to have a derivative of 0. Okay. So let's look at the mean value theorem. The mean value theorem, again, if I look at Rolle's theorem, we have f is continuous, differentiable, and the two endpoints are equal. When I look at the statement of the mean value theorem, it looks almost identical, except that it's only the first two conditions. F is continuous on an interval AB and differentiable on the interval AB. Okay, so we have weaker conditions. So the mean value theorem is a broader theorem, right? It applies in a broader range of cases, which means that the conclusion is going to be a little bit less specific, right? Here I am more specific about the functions I'm talking about, so I can have a more specific conclusion. Here the conclusion is a little bit less specific, but what that means is that anything that I can apply Rolle's theorem to, we can also apply the mean value theorem to. Okay, so let's go ahead and take a look at this, right? So we only have these first two conditions, f is continuous and differentiable, so we have a nicely behaved function. And that says there exists at least one number c where f prime of c equals this crazy thing. But if I look at that closely, that fraction on the right, f of b minus f of a, that's a difference of y values over a difference of x values, right? A and b are my x values. So that looks like slope. So here's a way to picture the mean value theorem. So here's my a comma f of a, here's my b comma f of b, and the function can do whatever it wants in between as long as it's continuous and differentiable. But what we're doing is we're saying, well, these 2 points I could connect with a line, right, a secant line connecting them, and that means that there has to be at least one point in between where the line is the same slope. Okay, so if I compare this to Rolle's theorem says these 2 points have the same height, so the line between them has slope 0, and there's a point in between with slope 0. And the mean value theorem is saying something a little bit more general. It's not being specific about 0, saying we can take 2 points with any heights, and they're going to have some slope connecting them. And that means that in between there has to be a tangent line with that same slope. All right, let's look at an example. F of x equals square root of x on the interval 0 to 9. So again, let's verify the hypotheses. So the first hypothesis, f is continuous on 0 to 9. And again, I don't want to spend a lot of time analyzing functions too deeply. We know the square root function, we know what it looks like, it's continuous. Okay, in general, root functions are continuous on their domains. And so we'll just say, okay, check. And 2, f is differentiable on the open interval 0 to 9. Again, I want to look at the derivative, right? So if f of x is root x, which is x to the 1/2, then f prime of x is 1/2 x to the negative half, which I can write as 1 over 2 root x. And here I can see we'd have a problem at 0, but for anything bigger than 0, we're okay. And we only need to be differentiable on the open interval 0 to 9, so that 0 point is not going to create a problem for us. Okay, so this f prime of x is defined on the interval 0 to 9. Okay, so there's our two conditions. Then there is a c in the interval 0 to 9, with f prime of c equals f of 9 minus f of 0 over 9 minus 0. So that's the square root of 9 minus the square root of 0 over 9 minus 0. Okay, which is 3/9 or simplifies down to 1/3. So this theorem is telling me that there is some point or some x value between 0 and 9 where the tangent line at that point has a slope of 1/3. Okay, so let's go ahead and find this. So we already computed f prime of x is 1 over 2 root x, and we want to solve f prime of x equals 1/3. So 1/3 equals 1 over 2 root x. Okay, so I'm going to solve by multiplying both sides to get rid of the denominators. So multiply both sides by 3 and multiply both sides by 2 root x. So on the left, the 3's cancel. On the right, the 2 root x's cancel. You might have called this cross multiplying when you were taking algebra. So 2 root x is equal to 3. So root x equals 3/2. And then if I square both sides, x equals 9/4. So c equals 9/4 is the value we are looking for. All right, and that's between 0 and 9, right? That makes sense. That was guaranteed by the theorem. Okay, now let's take a look at what the mean value theorem is going to give us in the future. And in particular, what we want to do is look at some things that it sort of shows for us, right? So a corollary to a theorem is you could think of it as a theorem, but it's a theorem that's kind of trivially true based on what's already been proven, right? So it's kind of like a free gift. I think that's what corollary means in Latin. I don't know Latin well enough, but the idea is that this is kind of a freebie theorem based on what we've already proven. Now, we didn't actually prove the mean value theorem, and we won't. I don't think that I think it's a little bit too complicated for us right now. You can see a proof of it in the book if you want to go through it, but I don't want to go through it on this video because I don't want you to think that this is something I'm going to test you on later or require. But what we will do is we'll prove these corollaries, and I think they'll help you understand them a little bit better. They're nice and simple. So our first corollary, let f be differentiable over an interval I. If f prime of x equals 0 for all x in I, then f of x equals c, a constant for all x in I. So what this is saying is that if the derivative is 0 everywhere, then the function is constant, okay, or at least on the domain that we're talking about. So first, what I want to do is show that this meets the criterion to be able to apply the mean value theorem, right? Let's just do a quick proof. Okay. F is differentiable. I know from the chapter on derivatives, when we talked about differentiability, that if a function is differentiable, then it is also continuous. So it's also continuous on the interval I. That's what we need for the mean value theorem. We need continuous and differentiable. Now maybe I is a closed interval, and maybe this function is differentiable at the endpoints. When we have something like the mean value theorem, we just need it to be differentiable at least on the open interval AB. If I look at something like the square root function, we can take derivatives at 9, that's fine. We only need it at least on the open interval. It's okay if the conditions are satisfied on a greater domain, right? Okay, we have the conditions for the mean value theorem. So by the mean value theorem, there is a C with f prime of C equals f of b minus f of a over b minus a. Okay. And if f prime of c is always 0, okay, then that means that if I take any number in between a and b, right, derivative is always 0, so I have 0 equals this thing. Well, if I multiply both sides by b minus a, that means that 0 equals f of b minus f of a, or another way to write that is f of b equals f of a. Now the idea is that I could pick any interval a, b that I want. I could pick any 2 points that I want in the interval I and apply the mean value theorem and show that f of b equals f of a. So this works for any pair of points a and b in the interval I. So if I say, okay, mean value theorem, go to work on all infinitely many pairs of points that you can have, I can show that any 2 points you pick in the interval are, function values equal, then it has to be a constant because everything is equal, right? So f of x equals c. All right. All right, let's look at the next corollary. All right, so constant difference. If f and g are differentiable over an interval I, and f prime of x equals g prime of x for every x in I, then f of x equals g of x plus c for some constant c. This is going to be something that is very important in chapter 5. Okay, so we're going to use this later, but this comes from the mean value theorem. Okay, so let's see if we can prove this again, or, like we did the first corollary. And what we're going to do is say, well, it's a corollary to the mean value theorem, so let's apply the mean value theorem. So just like the last one, right, if it's differentiable, then it's also continuous. Okay, so here's what I'm going to do, though. I'm going to work with one function instead of two. F and g are two different functions. We don't have two functions in the mean value theorem, there's just one. So what I'm going to do is I'm going to create a new function, a third function called h. So if I define h of x to be f of x minus g of x, if f and g are differentiable, then h of x is differentiable. And if it's differentiable on I, then it's also going to be continuous. And if h is continuous and differentiable, then we can apply the mean value theorem. So here's what we're going to do. Notice that h prime of x is f prime of x minus g prime of x. And I know that f prime of x and g prime of x are equal. So that's equal to 0 for all x and I. And I don't even need to go to the mean value theorem. I can just go back to corollary 1 and say, well, if the derivative of a function is always 0, then that function is constant. So by corollary 1, h of x equals c for some constant c. So then f of x minus g of x equals c. So that means that f of x is g of x plus c for all x and I. And that's exactly the statement that we wanted to prove. So we're done. Let's look at the last corollary. This corollary is something that I think that we already sort of knew. This is something that we've already talked about. So what we're going to do is just show maybe another way to get to the same conclusion, right? We've talked about how if a derivative is positive, the function is increasing. And if a derivative is negative, then the function is decreasing. And we sort of just gave an appeal to the graph in order to believe that, right? We looked at a graph and said, oh, okay, if the function is decreasing, that means the tangent lines must be sloped down. That's the only way to do that. So what we're going to do now is we're going to show this using the mean value theorem and not appealing to a graph. So again, we're starting with the conditions exactly necessary for the mean value theorem, right? F is continuous on the closed interval AB, differentiable on the open interval AB. So if I look at situation 1, assume that f prime of x is positive on AB, okay, then by the mean value theorem, there is a C in AB with f prime of C equals f of B minus f of A over B minus A. And I know that the derivative is always positive, so this f prime of C is positive. Okay. And if this is an interval AB, then B minus A is a positive number. So this implies that f of B minus f of A is positive, which implies that f of B is greater than f of A, which is exactly what it means for a function to be increasing. Okay, and the second one is the exact same way, except that the inequality goes the other direction, so it's decreasing, right? So this isn't something that's going to tell us something new about functions. We've already seen this, but we had to rely on a graph before to understand this, and here we can see, oh, okay, this is sort of confirming things with this mean value theorem. Okay, and that's really what the mean value theorem is going to do. It's making the logic solid for things going forward. Okay, so we're not going to have a lot of homework in this section. We're just going to have a few so that we can understand these, and we're going to use the mean value theorem to prove more important things like the fundamental theorem of calculus and as a tool to help us develop integration. All right, that's it for the section.